Hello everyone, this is Mr. 13 Things, or Silence It Good, following up after a video where I looked at extrude in Inventor, and now we're going to kind of look about the idea of rotate, or actually revolve. And what revolve is going to involve is going to be Quaternion math. And you can look around a number of other places, but essentially revolve is going to involve Quaternion math. It could also be Euler angles or anything else, but the Quaternion math is going to allow us to really be able to revolve around any, or rotate, revolve, or rotate around any arbitrary axis. Any axis. And the axis is going to be defined as usual. The axis will be defined by a vector that is going to be the unit vector. So this is going to be something, for instance, it might be 1, 0, 0 as to what we're used to writing. But later on, that's going to end up, and what we're used to writing is 1, 0, 0, and then remember that 1 chaser? Well, that's going to look completely different when we start getting into quaternions. And what it's going to look like is going to be a real vector, a real value, and then a vector, three-dimensional vector, which is going to look just like a four-dimensional vector. And this is going to be, you'll see later, a real value, which is equal to the cosine of the angle of revolution divided by 2. That's going to be there. And then this vector here is going to be the sine of the rotation angle divided by 2 times the vector of the axis times this vector here. Okay, so that's a whole lot of stuff maybe you didn't need to know, but the fact is what we're going to start doing is we're going to start using four dimensions or quaternions so we don't get involved in something called gimbal lock. So revolve is quaternion. So let's look at again the idea of having, and I'm not going to go through my red, yellow, and red, green, and blue, but we're going to say this is the x-axis, this is the y-axis, and this is the z-axis. In this case, I'll change my color very quickly to sketch out my face here, and I'm going to keep the same face that it did in the other one, and that is a face, and it's defined originally as points equal to 0, 0, 1. If we're going to use standard ordered pair notation, that's the z, and then 1, 0, 0, and then of course this one is 0, 1, 0. So standard notation of those are points. But now if we're going to actually rotate, for instance, we're going to take and maybe rotate about an axis, I don't know, we'll go ahead and rotate. For now, we'll just rotate about the z-axis here. So we're going to rotate about this z-axis here. So we're going to kind of take those points and turn them. So we're going to say we're going to rotate about the z-axis, rotate about z, my hand's cramping up here, about z-axis. We're going to rotate that 30 degrees. And in a positive way, which you're going to see later, would be counterclockwise. So how do we go about doing that? Well, basically the way you go about doing that is using something called the sandwich product. And there's other videos on that you can look at, but in this case we'll kind of lay out what becomes the lattice method twice. And I'm going to go ahead and pause here because my arm is really cramping up. So I paused, it's not going to help, but I'm going to continue here. So the lattice method is what we call it. It's going to be, in all effect, it's going to be abstracted to a basic calculation, but here's what it looks like. You're going to put your points, and I'm going to do this point here, you're going to express your points as a quaternion, right, on this side, and this is going to be real x, y, and z. And the point in this case is going to be, we're going to put 0 there, so that's kind of the space filler, and then in this case it's 0, 0, 1. Right, so this is your vector. right? That's what you're doing for the point, and you're going to actually, here you're going to have a quaternion, which is going to be the cosine of alpha over 2, and of course the cosine of alpha over 2 is the cosine of 15 degrees, and the cosine of 15 degrees is the square root of 6 plus the square root of 2 over 4, believe it or not. And then the sine of alpha over 2 times the unit vector, and the unit vector, remember, would be 0, 0, 1, because this is straight up the z-axis, and so you would have 0, 0, and then this would be the square root of 6 minus the square root of 2 over 4. So as you go through this calculation, you're going to end up with effectively some real, some I, some j, and some k when you go through the fact here of quaternion multiplication, when you know that a real times a real is a real, so these will all be real values. This is real here, and that's real, and then I times I is real, and this is real, and this is real, and then you're going to have some j's and some k's, and look at another video to do that, but you're actually doing a quaternion multiplication and coming up with an answer here the first time, and you're going to take that value and plug it back in. Whatever comes out of that is going to go into here. And then you're going to do, this is why it's called the sandwich product, and then you're going to multiply that value times the conjugate of this, which in this case is going to be still, the conjugate is still going to be the square root of 6 plus the square root of 2 over 4, and then negatives to all these, and by the time you end up making that negative, you have, this is going to be 0 here, and this is 0, and this is going to be the square root of 2 minus the square root of 6 all over 4. When you go ahead and do that whole process here, you'll end up with something that's going to be something real, probably 0, and the ijk, so what you got out of this is your rotated point. And in reality, when we're doing this, we may be actually intermittently rotating every 30 degrees, every 15 degrees, so you get a bunch of points around there. So this is just a wide overview of quaternion rotation, which effectively is done using the sandwich product. Right? Later on, you're going to see quaternions are also good for doing reflections and whatever else, but the idea of a sandwich product, and what it comes down to is you express your point, and this is a key thing here, as opposed to expressing your point as we've learned in the past of, you know, x, y, z with a 1 chaser over the top. You express your point as a 0 chaser in the front, or a 0 leader x, y, z. And so that becomes your kind of vector that you end up plugging in to start. And when you're done, again, you pull out these last 3 to get your point. And that would then rotate this thing 30 degrees positively, and so this thing would swing around here, and this would swing around, and this you'd see would stay the same. So you'd probably get something that looked in 3D space, something like this. And that would do the rotation on the face. Now in this case, it might be a real useful thing just to rotate this, in effect, 90 degrees, 90 degrees, 90 degrees, and you would get kind of that, you know, kind of basically that kind of diamond there or something like that. And that would be a good, useful way to do it, just have it rotating 90 degrees. That would give you a nice visual, and that the math would work. It's more likely that you might be wanting to rotate something out from some arbitrary axis here. And in that case, you'd first do some translation, then do your quaternion rotation, and then replace it back to where it started. So the concept of stepping into 4 dimensions comes to the fore here, and then when you add time, you're kind of in 5 dimensions, because you can very quickly, you can see where the animation comes in here, that as opposed to something that's a hard value here, this is just, could be just the cosine of some basically angular value, angular speed, you know, alpha over 2 times some time function, and you could all of a sudden start figuring out what's happening with quaternion rotations. So not very bad, actually. It's all based on some basic values, in this case for Hamiltonian numbers, I squared equals minus 1, J squared equals minus 1, and K squared equals minus 1, and I, J, K equals minus 1. So it's a little different than standard complex math on the complex plane, but not so bad that it can't be fixed by learning how to use the lattice method pretty well. And I'll link you back to that video to do that. So now we've learned out how to extrude something and how to revolve or rotate a point. And from there, all of a sudden, you're getting very close to understanding what's going on with Inventor. And we'll go ahead and do this one in SketchUp as well. And we'll kind of, once we get the kind of program, which is easily built here, this is somewhat easily done on a TI-83 calculator with a little bit of programming, but just as easily done in a spreadsheet or abstracted into a routine in Ruby or some other language. Thanks for listening.